Okay, so Poisson distribution, day number 8. We only have one more day on normal, and then it's test time. Again, I'm going to cross my fingers when I say this, knock on wood. This chapter has gone pretty well considering my expectations going into it. I was expecting a lot more pain on my part. Maybe the pain is just simply in the seats right now. I don't know. Thumbs up or thumbs down to pain? You like pain? Pain equals gain. Pain equals gains. Yep. Okay. So Poisson is going to be very similar to binomial, okay, but different in some ways. It's win or lose, success or failure. Probability stays the same from trial to trial, so there's no change. It's not dependent on, replacement or not replace. It's the same every time. However, binomial, you have a finite number of trials. So it might be like, I'm going to flip a coin and I'm going to flip it 10 times. Okay. Or probability that a car passes. Well, that's a bad example. Don't ignore that. That's going to be what we do over here. But over here, we have no limit to the number of trials, and it's typically based on time. So let's say that we see, I don't know, we're really bored. We sit on the side of the road, in a semi-busy road, and we record. We're some kind of traffic engineer, and we're like, we want to see how many cars come by here in an hour. Right? So on average, let's say half a car comes by an hour. Wait a minute. How about one car every 2 hours? How about that? Okay. But that technically would be half a car an hour, right? So we could use this and say, okay, what's the probability that less than 5 cars come by in a 3-hour period? Right? There's no limit to the number of trials, right? Because time is not the time doesn't limit the number of trials. Right? So it's a continuum of time. Now the formulas that are used, we saw this yesterday. Probability that x equals some value. We used combinations. We used probability of success to the x power, probability of failure to the n minus x. Today's formula, and I'm not going through the proof, A, because I don't want to, and B, because it looked really painful, is the probability that x equals some value. So let's say 3 cars come by in a 1-hour period, probably a low probability, right? If half a car per hour drives by, the probability that 3 come by, going to be slim to none. So what we do is we take e to the negative mu, that is mu, times mu to the x over x factorial. That's your friend or your acquaintance. All right, couple other things. The reason we like Poisson is because we didn't like binomial because we had to find the expected value, variance, and standard deviation separately. But in Poisson, the expected value is the variance, and it is mu. So you find it all in one. You'd still have to find the standard deviation. All right, so your standard deviation of x would just be the square root of mu. Okay, which is the square root of the variance. Yeah, Austin. Mu, I'm gonna teach you what mu is. I haven't taught you that yet. Okay, so let's look at this situation here. We're gonna look at it in the binomial sense and then in the Poisson sense. So if you have a 20% chance that an arrow you shoot hits a target, what are the chances of hitting it twice in 3 attempts? Well, probability of success would be what? 0.2. Probability of failure is 0.8. Number of trials is what? 3. And what does x equal? Yeah, we want to know when x equals 2. So I could do this the long way, and I could go 3 choose 2 times 0.2 to the 2 and 0.8 to the 1, right? Or I could do binomial PDF. What were the numbers we placed in here? Probability is in there, but there's 3 values I plug in. What are they? Number of trials, probability of success, number of successes, right? And then we could find our value. Easy, right? Binomial, done. Okay, so Poisson, here's how this problem would be worded if it were Poisson. Given 0.2 arrows hit a target per minute, Okay, based on some observation, what are the chances of hitting it twice in 2 minutes? So here's how we find mu. We get this thing lambda. Lambda is our rate. Lambda is your rate. So in this case, it'd be 0.2 arrows per minute. Mu is going to be lambda times the amount of time, as long as it's in the same units. Right? So if I said in 2 hours, you'd be like, yeah, we got to do a little conversion here. Oh, not that bad. Right? 120 minutes. So what would mu equal? What's 2 times 2? 4, move the decimal, 0.4. Right? So mu would equal 0.4. Now on paper one, this would be a non-calculator problem. How would we do that? So probability of x equal 2, we would take e to the negative mu times mu to the x all over x factorial. So let's remind ourselves what these things are. This right here is negative mu. That right there is mu. This right here is x. This right here is x factorial. Okay, just plug and chug. Now, let's see how they would want you to simplify this. Let's see. I don't know if this would be a problem they'd give you on paper one, just because it can't be simplified very nicely. But this would be, what would that be? 0.04 over 2e to the negative, 2e to the positive 0.2. Okay. Yeah. Did I mess something up? Did I do it wrong? Oh, shoot. Was mu 0.4? Okay. So that was 0.4 and that was 0.4. Okay, my bad. So then this would be 0.16. Thank you for that. That was pleasant. Carl, you sniped me, but then you helped me. 0.4. That's one way that you could write that in simplest form. Now, we can also use this PDF, CDF thing here. If I wanted to find the answer to this problem, would I use PDF or CDF? PDF, I just want one value. Okay, and now when you open up your calculator, it's going to ask you for 2 things, lambda, and then it's going to ask you for x, I think. Okay, now, okay, I've seen this go both ways with how it was presented. I want you to ignore the lambda and pretend it's mu on your calculator. On your calculator, okay? Ignore it and call it mu. So this would be 0.4 and this would be 2. Okay, pull up your calculator. Let's see what we get for the probability. Let's see what we get here. I'm getting a 0.054. With me? Okay, so the chances that in 2 minutes you hit 2 targets is about 5.5%. So this individual who hits 0.2 of a target per minute probably said, okay, let's get some stuff here. And they're like, once I hit the target once, and how long did it take them to hit the target once? If they got 0.2 targets per minute, 5 minutes. They went for 5 minutes, just Legolas, just. Ah, no, no. Ooh, that had to hurt. And then finally they hit the target because, yeah, luck and language. My son this morning pulled an iron off the table and hit himself in the face. That was cool. No, it was room temperature, fortunately. But he just saw a cord, yanked it, it slapped him in the face. I was laughing because I'm thinking Home Alone, right? Yeah. Okay, so in part B, at least 3 cars passed during the 2-hour period. So find lambda. What would lambda be? Let's start that piece together. 0.4 per hour. 0.4 cars per hour. How long is the time period? 2 hours. So I'm going to see a 0.8. So mu equals 0.8. I'm going to give you some time here to try to complete this problem on your own. Ready? So, yeah. Zero factorial is 1, right? Right. So it always accumulates to the left of the value you pick. What it does by itself. Yep. Yeah. Get used to the 0 factorial equals 1. That's critical and doesn't make any sense. Yeah, I hear you on that. Okay. In the second piece here, we want the probability that x is greater than or equal to 3. Now, we know that the sum of all these probabilities has to equal 1. What would this represent? This would not be a paper 1 question, part B. CDF, right? So that piece right there would be Poisson, Philip, CDF what? Yep, what numbers? Nope. 0.8. Yep. No, that'll include 3. So we want 2. Right? So then what this will do, we'll subtract that to the other side. So 1 minus that value will give us the probability that x is greater than or equal to 3. Okay. Over here, this could be a paper 1 question, and that would be a sufficient answer. If you know e to the negative 0.8 in your head, good for you. That's weird. Okay? But if they ask you this on paper 2, jump straight to Poisson's PDF of 0.8 comma 0. Poisson PDF. They don't give you points for that? Interesting. I'll have to look into it some more, but do we get answers here? Sorry, you got a question?
Yeah, I'm just wondering, so like...
First one, 0.449. Okay, and second one? 0.09.
But you have to subtract...
You got to take 1 minus said item. Okay. 0.47. I'll stop there. Okay, cool. And make a logical, just reason with it for a second. Like, if only 0.2 cars are going by during that period, and you're talking greater than 3, that number is probably going to be small. Right? So think about it logically before you circle or bubble your answer. Okay, last thing I want to do here is I want to go over this, and this is a funky problem, so I've actually written it all out, and you can watch the recording. I don't write any of this down right now. But on average, it's found that 8 out of every 10 components produced from a large batch has at least 1 defective component. Find the probability there's at least 2 defective components from a randomly selected batch. So we don't know mu. I looked at this problem for a while. I didn't want to look at the work, but I looked at it for a while and was like, am I supposed to know mu right now? Like, I don't know what's what. But think of the 8 out of 10 as a probability that we've selected at least 1 defective component. So that would mean that the probability that x is greater than or equal to 1 is 8/10. So what probability have we not involved in that? Probability that x equals, which is 0. That's the only probability we don't have. So technically, probability that x is greater than or equal to 1 is 1 minus the probability that x equals 0. With me? Okay, so now I'm going to move some things around here, and I see that 2/10 equals the probability that x equals 0. Now from there, I know this, e to the negative mu equals mu to the 0 over 0 factorial, but I don't know what mu is, but I'm going to figure it out. And you might anticipate what happens when we have a variable and an exponent of a exponential function. Yeah, natural log. So I know that, right, because 0 factorial is 1 and mu to the 0 is 1. So the natural log of 2 equals negative mu. Therefore, that's mu. That's gross. Yeah, Emma. You will in a moment. Well, technically speaking, it could be time or an unlimited number of potential, in this case, a large batch of components. There's no limit on the number of components, right? So large batch means unlimited interval. Doesn't say 10 components, then we'd think binomial. All right. So then to find probability that x is greater than or equal to 2, all right, I know this. That's going to be 1 minus the probability that it's less than 2. And then if it's paper 1, you can't use a calculator. You can't use the old CDF, PDF. This is what I would write. That'd be a paper 1 answer. Plug in the value for 0, for mu, for 1, and simplify as far as you can. I'm not going to simplify that further. But using the calculator, oh, that's a lot easier. Right? And I don't know what the answer to that is, but I didn't calculate it. Can somebody do that for me? Negative natural log of 0.2 comma 1. Let me know when you got one there. Hugo, do you have an answer? 0.3218. Somebody else confirm? 0.3218. Okay. So that means in a large batch of components, I don't know how many a large batch is, but the probability that at least 2 of them are defective is said thing, 0.3218. So that's Poisson. Typically, they'll tell you whether or not it's Poisson in the homework. I'm not going to go into any of these problems because I want you guys to get max work time. But all of it's posted. Looks like this is probably binomial. I think I tell you right there. It's shrunk down for you. It's probably hidden in a tree somewhere like Marky Mark. Here, oh, Poisson. So you'll use Poisson, et cetera, et cetera. So we'll call that good for today. I'll get some donuts out here and we can